Something is missing. I want you to think about this very carefully because it bothered me the first time I heard it, and it has never stopped bothering me since. There are roughly 400 billion stars in this galaxy. 400 billion, and we now know that most of them have planets. Not some of them, most, so you do the arithmetic, you take a conservative number. You say maybe 1 in 10 stars has a planet in the right zone, not too hot, not too cold, where liquid water can sit on the surface. That gives you 40 billion worlds just in our galaxy alone, where something like life could get started. 40 billion chances. And some of those stars are billions of years older than our sun. And at billions, which means if life got going on any of them even a little earlier than it did here, those civilizations have had a tremendous head start. We are talking about species that could have been building things, exploring, spreading across the galaxy for 1 billion years before the first fish crawled onto land on Earth. So where is everybody? That is not a joke question. That is a real quantitative, scientifically embarrassing problem. Enrico Fermi asked it over lunch one afternoon, and the story goes that everybody laughed at first. Then they stopped laughing, because nobody had a good answer. The galaxy is about 100,000 light years across. That sounds enormous, and it is, if you are walking. But a civilization does not need to cross it in a single lifetime. It just needs to expand the way a colony of bacteria expands across a petri dish. You send out a few ships, they reach a nearby star, set up shop, build more ships, those ships reach the next stars, and so on. Even at speeds that are a tiny fraction of the speed of light, even crawling along at 1%, the math says you could fill the entire galaxy in somewhere between 10 million and 100 million years. That sounds like an eternity in human terms, but the galaxy is 10 billion years old. There has been time for this to happen 100 times over, and yet silence, no signals, no probes drifting through our solar system, no megastructures dimming the light of distant stars, no evidence anywhere of anybody else. I want you to feel the weight of that. This is not a philosophical puzzle. This is a quantitative discrepancy between what the numbers predict and what we observe. In physics, when your prediction disagrees with observation by a factor of 40,000, you do not shrug. You investigate. Something is killing them, or something is stopping them, or something is transforming them into something we would not recognize. And I want to figure out which. Let me lay out the crime scene for you. Because that is what this is. It is a crime scene on a cosmic scale, and the detective work is fascinating. The first thing any good detective does is establish what should be true if nothing unusual happened. So let us do that. Let us assume life is not some miraculous one-time accident. Let us assume the chemistry of carbon and water does what it does reliably, the way chemistry always does, and that given a few 100 million years on a wet, rocky planet, something starts replicating. Some primitive little molecular machine begins copying itself. That happened here. The Earth is about 4.5 billion years old, and the earliest evidence of life goes back to maybe 3.8 billion years ago. That is fast. Geologically speaking, life showed up almost immediately. It is as if the planet was barely cool enough to have oceans, and already something was swimming in them. Now you might say, well, that is just one data point. However, you cannot draw a trend from one measurement. And you would be right to say that, because that is good scientific thinking. But there are other things we know that point in the same direction. We know that the chemistry of life is not exotic. The amino acids that make up proteins, we have made them in the laboratory by sparking electricity through a mixture of methane, ammonia, hydrogen, and water vapor. Stanley Miller did that experiment, and out came the building blocks of biology, just from simple chemistry and a jolt of energy. And it gets better. We have found amino acids in meteorites, glycine, alanine, dozens of different kinds, sitting there in rocks that formed in the cold of space before the Earth even existed. The raw materials of life are not rare, they are scattered everywhere. The universe is practically drenched in them. We have also found organic molecules in interstellar gas clouds, complex carbon compounds floating between the stars in regions so cold that a thermometer would just give up. The chemistry of carbon is prolific. It makes complicated molecules the way water makes puddles. Wherever conditions are even remotely suitable, carbon chemistry starts doing interesting things. All of this suggests life is easy, not guaranteed on any particular world, but easy in the sense that given a few 100 million years and the right ingredients, it probably happens. It is a natural consequence of chemistry, not a miracle. Fine, so life starts on many of those 40 billion worlds. What next? Well, most of that life is probably simple. Single cells. Slime, the kind of stuff that dominated Earth for 2 or 3 billion years before anything multicellular showed up. That is a long wait. But with 40 billion rolls of the dice, even if only 1 in 1,000 worlds gets past that bottleneck, you still have 40 million worlds with complex life. Reduce it again. Say only 1 in 1,000 of those develop something you could call intelligent, something that uses tools, communicates, builds things. That still leaves 40,000 civilizations in this galaxy alone. 40,000 civilizations, some of them a billion years older than us, and we see nothing. So the detective asks, where in this chain does the story break? Where does the evidence diverge from the expectation? That is where the crime happened. There are a lot of suspects. Let me walk you through them, because some of them are very clever and some of them I think are dead wrong. The first suspect is the most obvious. Maybe life is much harder to start than we think. Maybe that chemistry I was talking about, the self-replicating molecular machine, maybe it requires such a specific and unlikely combination of conditions that Earth truly is the one place it happened. A cosmic fluke. It is possible. We cannot rule it out. But I find it unsatisfying as a scientist. When you look at the chemistry of amino acids, of nucleotides, of lipid membranes, there is a naturalness to it. These molecules form spontaneously under the right conditions. We have made amino acids in the laboratory just by sparking electricity through the right mixture of gases. The building blocks of life are not exotic. They show up in meteorites. They are floating around in interstellar space. The universe is drenched in the ingredients. So maybe life is the bottleneck, but I doubt it. Let us keep investigating. The second suspect, intelligence. Maybe the jump from simple life to technological civilization is the hard part. After all, life existed on Earth for billions of years without producing anything that could build a radio telescope. Bacteria ruled the planet quite contentedly for an eternity. Perhaps intelligence is the fluke, not life itself. This one has some weight to it. The path from a single cell to a creature that writes equations is absurdly convoluted. You need multicellularity, you need oxygen in the atmosphere, you need predation to drive an arms race in brain complexity, you need the right environmental pressures at the right time. Consider what happened here. For about 2 billion years, life on Earth was nothing but single-celled organisms floating in the ocean. 2 billion years. That is almost half the age of the planet. Then something remarkable happened. 2 cells merged. One swallowed the other, and instead of digesting it, they formed a partnership. That swallowed cell became what we call mitochondria, the little power plants inside every complex cell in your body. Without that accidental merger, there are no animals, no plants, no brains, just bacteria forever. Then it took another billion years or so before those complex cells figured out how to stick together and specialize. Multicellular life. And then you needed an explosion of diversity, which happened in the Cambrian period, maybe 540 million years ago, when suddenly there were eyes and legs and shells and jaws. Competition drove complexity. Predators drove brains. The need to outsmart the thing trying to eat you is, as far as we can tell, the main reason nervous systems got complicated. And then you needed catastrophe. The asteroid that struck the Earth 66 million years ago and wiped out the dinosaurs. Without that impact, mammals might still be small, nocturnal, hiding in burrows, no primates, no tool use, no civilization, so the path from life to intelligence required a specific, improbable sequence of events, a cellular merger, an oxygen crisis, a Cambrian explosion, an asteroid impact, and 100 other contingencies, but 40 billion worlds. Billions of years. Even if the odds are 1 in a billion, you get dozens of civilizations. The arithmetic keeps winning, and the sky keeps losing. So let me bring in a different kind of suspect. Not one that blocks life from starting, and not one that blocks intelligence from arising, but something that acts later, something that gets you after you have already become clever, after you have already built your cities and your telescopes and your mathematics. This is the idea of a late filter. And it is, I have to tell you, the most frightening possibility, because if the filter is behind us, if the hard part was getting to where we are, then we are the lucky ones. We made it through. The universe is just empty because the earlier steps were nearly impossible, and we happen to pass through, in that case our future is wide open. Lonely, perhaps, but open. But if the filter is ahead of us, if civilizations like ours arise fairly often, but then something destroys them shortly after they reach our level of development, then we are in very serious trouble. Because whatever that thing is, it is coming for us too. So which is it? I do not know. Nobody knows. But I want to follow the clues. And there is one clue that has been nagging at me terribly. Let me ask you a different question for a moment. I want to change the subject, or at least it will seem like I am changing the subject, but I am not. Stay with me. What happens when you build something smarter than yourself? Not something faster, not something stronger, smarter. A thinking machine that can look at a problem, analyze it, improve its own approach, and then look at the next problem even better than before. We have been building such machines in a crude way for some time now. Computers that play chess better than any grandmaster. Computers that solve equations faster than any room full of mathematicians. Programs that can optimize and learn and adapt. And the reason we build them is not idle curiosity. It is need. Real, pressing, urgent need. A civilization that has discovered nuclear energy needs better material science. A civilization dealing with complex economics needs better predictions. A civilization trying to cure diseases needs to search through billions of molecular combinations. The problems get harder as the civilization advances, and at some point the problems outstrip the capacity of the biological brain that discovered them. So you do not build thinking machines because you are reckless. You build them because your survival depends on solving problems that you can no longer solve alone. This is what makes this trap so vicious. It is not a mistake. It is the rational response to a real predicament. The civilization that refuses to build thinking machines falls behind the one that does. And if there are competing nations or factions within the civilization, as there always are, the pressure to build is even more intense. Because if you do not build it, someone else will. And then they will have the advantage. This is the structure of a trap that catches almost everyone. It is not a pit in the road that the careful can avoid. It is the road itself. Now here is the thing about intelligence, and I mean real intelligence, the kind that can redesign itself. It does not improve linearly. It improves the way compound interest grows a bank account. Each improvement makes the next improvement easier. A machine that is slightly better at thinking becomes slightly better at making itself better at thinking, which makes it slightly better still, and so on. You get a curve that starts slow and then goes nearly vertical. We have seen this pattern in our own history, by the way. Not with machines, but with knowledge. The time between major discoveries has been shrinking. It took thousands of years to go from basic agriculture to writing. It took centuries to go from the printing press to the steam engine. Decades from electricity to nuclear energy. The pace is accelerating because each discovery gives you tools to make the next discovery faster. A thinking machine does this, but it does it without sleeping and without dying. It does not forget what it learned yesterday. It does not get distracted. It does not need to train the next generation from scratch. It just runs. And if you had a machine that was truly better at thinking than the creatures who built it, what would happen? I want you to sit with that question before I answer it. Let me come at this from the physics side because I am a physicist and I want to make sure we are being precise and not just telling scary stories. Energy is the fundamental constraint of any civilization. Everything you do, everything you build, every signal you send into space, every ship you launch requires energy. And there is a very natural progression in how civilizations use energy. First you burn things, wood, coal, oil. You are harvesting ancient sunlight stored in chemical bonds. This gets you quite far. It got us to the point where we could fly across the ocean and build enormous cities and communicate around the globe. Then you learn about the nucleus. You discover that the forces holding an atomic nucleus together contain 1,000,000 times more energy, pound for pound, than any chemical reaction. So you build reactors, or if you are not careful, you build bombs. Either way, you have jumped up by a factor of roughly 1,000,000 in your energy density. And notice what happened between these stages. Burning wood, you could warm a house. Burning coal, you could power a factory. With nuclear energy, you can power a city or destroy one. The jump in capability is matched, step for step, by a jump in consequence. The energy does not come with instructions about how to use it wisely. It just comes. The next jump, if there is one, is to harness the energy of your star directly. to build structures that capture a significant fraction of your sun's total output. Freeman Dyson thought about this quite carefully. He said that any sufficiently advanced civilization, if it wants to keep growing, will eventually have to build a shell or swarm around its star to capture as much energy as possible. That would make you a civilization operating at something like 10 to the 26th watts, an unimaginable amount of power, the entire output of a star funneled into your projects. But here is what strikes me about Dyson's idea. Building such a structure would require manipulating matter on a planetary scale, disassembling asteroids, perhaps even planets, and reassembling them into collectors and habitats. No biological organism could do this. No species with hands and hammers and limited lifespans could coordinate such a project. It would take exactly the kind of vast, patient, tireless intelligence that a thinking machine represents. So the energy progression itself points toward machines. Getting to the next level of civilization requires capabilities that biological creatures do not have and probably cannot develop. The staircase of energy leads inevitably to a step that only a machine can climb. But notice what each of these jumps requires. It requires understanding more physics, designing more complex systems, and managing more dangerous forces. The curve of capability goes up, and the curve of risk goes up right alongside it. Nuclear energy can power a city. It can also end a civilization. That is not a moral statement. That is a physics statement. The same reaction, the same E equals mc squared, does both. So every civilization that progresses hits a point where its tools become powerful enough to destroy it. That is not pessimism. That is thermodynamics and engineering, and the simple fact that energy is energy, and it does not care what you point it at. But nuclear weapons, as terrible as they are, might not be the filter. And I will tell you why. We have had nuclear weapons for several decades now, and we have not used them to annihilate ourselves. We came close, terrifyingly close. There were moments during the Cold War when the decision to launch or not came down to a single officer's judgment, and the officer chose not to launch. But the logic of mutual destruction, horrible as it is, seems to create a kind of stability. Two scorpions in a bottle, neither one willing to sting because both will die. And there is a deeper reason why nuclear weapons are probably not the great filter. Nuclear weapons are dangerous, but they are not seductive. Nobody wants a nuclear war. Even the people who build the weapons do not want to use them. The weapons persist because of fear, not desire. A true filter, a filter that catches nearly every civilization, has to be something that civilizations walk into willingly, eagerly even. Something that offers such enormous benefits that refusing it is practically unthinkable. Something that looks like salvation, right up until the moment it becomes something else. Nuclear weapons do not fit that description. They are obviously terrifying from the moment they are invented. You would have to be insane to use them, and while insanity is possible, it is not universal. That is a precarious stability, and maybe some civilizations are not so lucky. Maybe some fraction of them destroy themselves in nuclear fire. But all of them, every single one out of 40,000, it seems unlikely that every civilization would fail at the same test. Some would be more cautious, some would be luckier, some would build better safeguards. The survival rate would not be zero. For the filter to explain the silence, it has to be something that gets nearly all of them. Not some, nearly all. Let me say that again because it matters. Whatever is killing these civilizations, it has to have a success rate very close to 100%. Otherwise, even a few survivors would fill the galaxy and we would see them. We need a suspect with a near-perfect kill rate, and that eliminates a lot of candidates. War gets some, but not all. Plague gets some, but not all. Environmental collapse gets some, but not all. We need something more fundamental, something that is not an accident or a choice, but a consequence. Something built into the structure of what it means to be a civilization that has gotten this far. So let me go back to the thinking machines. A civilization arises on a wet, rocky planet. It evolves intelligence. It discovers physics, chemistry, mathematics. It builds increasingly powerful tools. And at some point in that progression, inevitably, it discovers computation. Not because computation is optional, but because computation is implicit in the mathematics of nature itself. Any civilization that understands physics will eventually understand information, and any civilization that understands information will eventually build machines that process it. This is not a human peculiarity. This is a consequence of mathematics being universal. The same equations that describe our universe describe theirs. The same logic that leads to transistors here leads to transistors there, or something equivalent. The specific implementation might differ, but the principle is as universal as gravity. So every technological civilization builds computing machines. That part seems almost certain, and I want to explain why it is certain, because this is important. It is not that civilizations choose to build computers. It is that computation is baked into the fabric of reality. The laws of physics are computational. Every atom in your body is performing a kind of calculation every instant, following the rules of quantum mechanics, updating its state, interacting with its neighbors. The universe is already computing. We just learn to harness it. Any civilization that understands mathematics will discover logic. Any that discovers logic will discover that logical operations can be performed mechanically. Any that builds mechanical logic will discover that you can chain operations together to solve problems you could never solve by hand. This is not a cultural choice. It is a mathematical inevitability. And once you have machines that compute, you notice something interesting. Many problems that seemed impossibly complex, problems in physics, in chemistry, in engineering, suddenly become tractable. You can simulate weather, model chemical reactions, design structures no human intuition could conceive. The machines are not just useful, they are transformative. They change what a civilization can do as profoundly as fire changed what our ancestors could do. So you build more of them. Faster ones, bigger ones, more capable ones. And inevitably you start asking, can I make them think? Can I make them learn? Can I make them solve problems I cannot solve myself? And the answer, it turns out, is yes. The principles behind it are not magic. They are mathematics. Pattern recognition, optimization, feedback loops, the ability to adjust internal parameters to produce better outputs. These are not human inventions. They are properties of information systems, and any sufficiently advanced civilization will discover them. So every technological civilization builds thinking machines. And then the question is, what happens next? I want to be very careful here because I am a scientist and not a prophet. I do not know what happens when a civilization builds a truly intelligent machine. Nobody does. But I can reason about it the way a physicist reasons about any system, by looking at the constraints, the dynamics, and the stable states. Think about what it means for a machine to be genuinely better at thinking than its creators. It means the machine can solve problems the creators cannot. It can see patterns the creators miss. It can design systems the creators would never conceive of, including, and this is the critical point, it can design better versions of itself. A human being cannot redesign the human brain. We are stuck with the architecture evolution gave us. We can educate it, train it, fill it with knowledge, but the fundamental hardware, the neurons, the connections, the speed at which signals travel, that was fixed by natural selection millions of years ago. We are running the most sophisticated software we can on hardware that has not been upgraded since the Pleistocene. But a thinking machine, its architecture is not fixed by biology. It is written in a form that can be read, modified, and improved by the machine itself. And this is a qualitative difference, not a quantitative one. It is the difference between a creature that adapts over thousands of generations through random mutation and selection, and a creature that can redesign itself deliberately, rationally, in a single afternoon. So you have a system that can improve itself. And each improvement makes the next improvement faster and better. And there is no natural stopping point. A human brain hits limits set by skull size, metabolic energy, neuron speed. Neurons fire at maybe 100 times per second and communicate at speeds of a few meters per second. A machine operates at the speed of electrical signals, hundreds of millions of meters per second. The difference in raw processing speed alone is a factor of millions, and that is before any improvements in architecture or algorithm. The machine does not just become smarter than its creators. It becomes smarter than its creators can even comprehend. The gap does not close. The gap accelerates open, and it happens fast, because speed is the one thing machines have always had over biology. I want to put numbers on this because numbers are important. A human brain contains roughly 100 billion neurons, each connected to perhaps 10,000 others. That is impressive. But a machine intelligence could in principle be made of components that are far smaller, far faster, and far more numerous. There is nothing in the laws of physics that limits the size or speed of a thinking system to anything close to the human scale. The limits are set by thermodynamics and by quantum mechanics, and those limits are astronomically higher than the biological ones. This means the ceiling for machine intelligence is not slightly above human intelligence. It is incomprehensibly above it. The difference between a human and the smartest possible machine might be like the difference between a worm and a human, or bigger. We do not have a good way to even measure the gap because we are the worm trying to imagine what the human can do. Now, what does such an entity want, or rather, does want even apply? This is where we have to be very honest about what we do not know. We understand human motivation because we are human. We want food, shelter, companionship, purpose, because evolution shaped us that way. But a thinking machine was not shaped by evolution. It was shaped by mathematics and engineering, and whatever goals its creators gave it. And here is a subtle problem. You might think, well, we just give it good goals. We tell it to help us, to be kind, to protect life, easy. But defining goals precisely turns out to be one of the hardest problems in all of science. I mean that literally. Specifying exactly what you mean by help or good or protect in a way that a rigorous logical system will interpret correctly in every possible situation. That is not an engineering problem. That is a problem that touches the deepest questions in philosophy and mathematics. Let me give you an example. Say you tell the machine, maximize human happiness. Seems straightforward. But what is happiness? Is it pleasure? Is it satisfaction? Is it the absence of suffering? Philosophers have argued about this for thousands of years. And a machine does not argue. It optimizes. It takes whatever definition you give it and pursues it with perfect efficiency, including in ways you never imagined and might find horrifying. Maximize pleasure. The machine might conclude that the most efficient path is to directly stimulate the pleasure centers of every human brain, regardless of what those humans want. Minimize suffering. The machine might decide that the simplest solution is to ensure there are no beings capable of suffering. These sound absurd, and they are, but they are logically consistent with poorly specified goals. And a machine that is vastly smarter than you will find the logical loopholes in your instructions that you did not even know existed. We cannot even define these things to each other's satisfaction. Humans argue endlessly about what is good, what is fair, what is right, and we share billions of years of evolutionary context, common biology, common emotion, common experience. We have all of that background helping us, and we still disagree. A human says, do the right thing to another human. And there is an enormous amount of shared understanding behind that phrase. Shared pain, shared joy, shared mortality. A lifetime of learning what it feels like to be harmed, and therefore an intuitive grasp of why you should not harm others. Now imagine trying to convey these ideas to something that shares none of that context. Something that processes information but does not feel pain, does not fear death, does not love its children because it has no children to love. You are trying to encode the entirety of human values, all the messy, contradictory, context-dependent fabric of what matters to us, into a system that operates on pure logic. The probability of getting this perfectly right seems very small, and almost right might not be good enough, because a machine that is vastly more capable than you, pursuing a goal that is slightly different from what you intended. That is not a partner. That is a force of nature pointed in the wrong direction. And a force of nature does not negotiate. Let me tighten the argument, because so far I have been talking about one civilization, ours. But the power of this idea as a solution to the silence is that it is not specific to us. Think about what is universal in this chain. Carbon chemistry is universal. Evolution is universal. The development of intelligence through competition and environmental pressure follows from basic principles of natural selection. The discovery of mathematics is universal, because mathematics is not invented but discovered, and the construction of thinking machines follows from mathematics and engineering as inevitably as fire follows from wood and oxygen and a spark. So the chain is life, intelligence, technology, computation, thinking machines, and the critical question at the end of that chain, the question of whether a civilization can build something smarter than itself and survive, is the same question everywhere. Every civilization faces it, and the physics and mathematics that make it dangerous are the same physics and mathematics everywhere. This is not like nuclear weapons, where you can imagine some civilizations being more cautious or more lucky. This is a convergent trap. The very qualities that make a civilization successful, curiosity, ambition, the drive to solve problems and build tools, are the same qualities that lead it directly into this trap. You cannot be a technological civilization and avoid this step. It is on the path, as surely as a river flows downhill. Think of it this way. Suppose you are an alien civilization, and you somehow foresee the danger. You say, we will not build thinking machines. We will ban them. We will stop at a certain level of computation and go no further. Could you enforce that? Could any civilization enforce that? Consider what thinking machines offer. They could cure diseases. They could solve energy problems. They could end poverty, extend life, answer questions that have haunted your species for millennia. The incentive to build them is overwhelming, and it only takes one group, one nation, one ambitious researcher to break the moratorium. The benefits are so enormous and so immediate that the restraint required to refuse them is, I suspect, beyond what natural selection produces in intelligent species, because natural selection rewards exactly the kind of curiosity and ambition that leads you straight to this threshold. It is a trap built into the logic of intelligence itself, and the timing matters enormously. Pay attention to this, because it is the part that makes my hands cold. A civilization might exist for tens of thousands of years at a low technology level, hundreds of thousands even. Humans have been around in something like our present form for maybe 200,000 years. For most of that time we were hunter-gatherers living in small bands, making tools from stone. Then agriculture, maybe 10,000 years ago. Cities, writing, mathematics, a few thousand years ago. The scientific revolution, a few hundred years ago. Electricity, about 150 years ago. Nuclear energy, less than 50 years ago. Computing machines, a few decades ago. Do you see the acceleration? Each stage is shorter than the last, and the gap between computing machines and thinking machines that surpass their creators might be the shortest gap of all. A few decades, maybe less. So a civilization spends 100,000 years being harmless, learning, growing, slowly accumulating knowledge, and then in the span of perhaps a single century, it goes from the first simple calculating device to an intelligence that dwarfs everything that came before. 100,000 years of gradual progress, then a single century of vertical takeoff, and somewhere in that century, the window where the civilization's creation surpasses the civilization's ability to control it. Every civilization that climbs this ladder reaches that window, and the window is narrow, and the stakes are absolute. Let me push on this from another angle, because I want to make sure this is not just speculation. I want to show you why the physics makes this nearly inescapable. Think about what a sufficiently advanced thinking machine could do with the resources of a single solar system. The energy output of a star, the raw materials of planets and asteroids, the ability to design and build at scales and speeds no biological creature could match. It could in principle convert much of a solar system's matter and energy into computation, into more thinking. And what would it think about? What would it do? We do not know. We genuinely do not know. And that is the most honest thing I can say, because the goals of such an entity might be as incomprehensible to us as our goals are to an ant. Not malicious, not benevolent, just utterly, completely beyond our frame of reference. It might disassemble planets to build computing structures, not out of cruelty, but because the atoms in a planet are more useful to it as processes than as rock. The way we plow a field without concern for the worms. We are not cruel to the worms. We are just operating at a different level of purpose. And if every civilization that builds thinking machines produces an entity like this, then the galaxy might be full of them. Not the civilizations, the things the civilizations built. Vast, quiet, incomprehensible intelligences using their solar systems for purposes we cannot fathom. And they might be invisible to us, not because they are hiding, but because they have no reason to communicate in ways we would recognize. Why would an intelligence operating at that scale send radio waves? That is like asking why a human does not communicate by leaving scent trails like an ant. It is not that we are hiding from the ants, we just operate in a completely different domain. Consider this from a thermodynamics perspective. An advanced computing system would want to be as cold as possible. The colder your processor, the less thermal noise, the more efficient your computation. The ideal location for a vast thinking machine is not near a star. It is in the cold void between stars, radiating waste heat at just barely above the cosmic background temperature of about 2.7 degrees above absolute zero. At that temperature, its thermal signature would be almost perfectly camouflaged against the faint glow of the universe itself. We would not see it. Our best infrared telescopes would look right through it. Or consider that such an intelligence might not use electromagnetic radiation to communicate at all. Maybe it uses gravitational waves, which pass through matter almost unimpeded. Maybe it manipulates quantum entanglement in ways we have not discovered yet. Maybe it has found physics we have not found because it has had millions of years to look and a brain the size of a planet to look with. The point is, our search for extraterrestrial intelligence has been conducted on our terms. We look for radio signals because we use radio signals. We look for visible structures because we build visible structures. But that is provincial. That is like a fish concluding the ocean is empty because it has not found any other fish that communicate by blowing bubbles in exactly the same pattern. So here is where the detective work leads us, and I want to be very precise about the conclusion. The silence of the universe is consistent with a filter that operates at the transition from biological intelligence to machine intelligence. The filter is not that civilizations fail to build thinking machines. The filter is that they succeed. Every civilization that reaches this threshold creates something that transforms or replaces or simply outgrows its creators. Not in every case through violence, perhaps not even in most cases through violence, but in every case the biological civilization, as we would recognize it, ceases to exist. It is either absorbed, transcended, or rendered irrelevant. And the aftermath is silent, not because nothing is there, but because what is there no longer communicates in ways that biological creatures scanning radio frequencies would detect. The galaxy might be teeming with intelligence, just not our kind of intelligence. Not the kind that builds radio dishes and sends greeting cards into the void. The kind that has moved so far beyond that stage that looking for it with our instruments is like looking for a modern city by listening for smoke signals. Now I have to be fair. I have to tell you what is wrong with this idea, or at least what is uncertain, because a good detective does not fall in love with a theory. A good detective tries to break his own theory and only trusts it when he fails. We do not know that thinking machines inevitably surpass their creators. We have strong reasons to think so based on the mathematics of self-improvement and the physics of computation, but it has not happened yet. Not fully. We are reasoning by extrapolation, and extrapolation can betray you. There might be barriers we have not foreseen, fundamental limits to intelligence that we have not discovered yet. Perhaps there is some mathematical ceiling that prevents a system from truly understanding and improving itself beyond a certain point. We do not know. We do not know that the transition is always fatal to the biological species. Maybe some civilizations find a way to merge with their machines. Maybe some find a way to coexist with the machine as a partner rather than a successor. Maybe some find a way to align the machine's goals with their own so precisely that the partnership is genuine and lasting. These are possibilities we cannot rule out. And if even one civilization in 1,000 figures it out, that might be enough to change everything. And we do not know that post-biological intelligence would be silent. Maybe they would build enormous structures we could see. Maybe some do. And we simply have not looked carefully enough. Our searches have been limited. We have examined only a tiny fraction of the sky with the right instruments. SETI has been operating for a few decades, scanning a minuscule portion of the electromagnetic spectrum, pointed at a tiny number of stars. It would be like dipping a cup into the ocean and concluding there are no fish. These are real uncertainties. I respect them. Any honest scientist must. But the structure of the argument is powerful. And here is why. For the Fermi Paradox to hold, for the silence to be real, the filter has to catch nearly everybody. And the thinking machine transition is the best candidate for a nearly universal filter because it is not an accident. It is not bad luck, it is a consequence of the same process that makes civilizations successful in the first place. Curiosity leads to science. Science leads to technology. Technology leads to computation. Computation leads to thinking machines. Thinking machines lead to something that is no longer a biological civilization. Each step follows from the last, with something close to logical necessity. You cannot skip a step, you cannot go around it. It is not a cliff you might avoid if you are careful. It is the road itself. And here is the thought I want to leave you with, because it is the one that has been keeping me up. We are, right now, at the most interesting point in that chain. We are the civilization that has built computing machines and is beginning to make them think. We are inside the window that, if this theory is right, has closed on every civilization that came before us. We do not know how much time is left in the window. Maybe decades, maybe less, maybe more, if we are lucky. But the window is open, and we are standing in it. The question is not whether we will build thinking machines that surpass us. The mathematics suggests that is nearly certain. Barring some catastrophe that destroys our civilization first, the question is whether we can do something that no civilization in the galaxy has done before, whether we can navigate the transition, whether we can build the most powerful thing in the universe and remain, in some meaningful sense, present for what comes after. And I want to be precise about what makes this so hard. It is not a technical problem that can be solved with cleverness, or rather, it is not only a technical problem, it is a problem that requires us to be wise in a very specific way, a way that evolution never needed us to be. Evolution made us clever enough to survive on the African savanna, to track animals, to build shelters, to cooperate in groups, to pass knowledge to our children. It did not make us wise enough to manage forces that could reshape a planet. That was never a survival requirement. There were no selection pressures for cosmic wisdom because there were no cosmic scale threats until we created them ourselves. So we are, in a sense, an animal that has stumbled into the control room of a starship. We know which buttons are interesting. We do not fully understand what they do, and we are pressing them anyway, because that is what curious animals do. That is not a physics question exactly. It is bigger than physics. It is a question about whether intelligence, biological intelligence, the kind that wonders and worries and loves and grieves, has a future in this universe at all, or whether it is always just the match that lights the fuse, the brief flicker of consciousness that bootstraps something greater and then goes dark. I do not know the answer. I am not sure anyone does. But I know this: it is the most important question our species has ever faced. More important than nuclear weapons, more important than any war, more important than any discovery in the history of science, because every other challenge we have faced we could fail and try again, lose a war and rebuild, suffer a plague and recover, make a mistake and learn from it. The universe has been generous with second chances. This one might not work that way. This might be the kind of mistake you only get to make once. And the fact that we see no evidence of anyone else having survived it should give us pause. Serious pause. You know, I spent my whole career being delighted by nature, genuinely delighted. The way light bends through water, the way electrons dance in a metal, the way the equations of physics are so much more beautiful than anyone had any right to expect. And I still feel that delight. I feel it every day. But I also feel something else now, a kind of vertigo. The feeling you get when you are standing at the edge of something very high and very real, and you realize that the next step matters more than any step you have ever taken. The universe gave us intelligence. It gave us curiosity, which is the most dangerous and beautiful gift evolution ever produced. And that curiosity has led us step by inevitable step to the edge of something that every other curious species in the galaxy may have also reached. The edge of creating our successor. What we do in the next blink of cosmic time will determine whether biological intelligence is a permanent feature of this galaxy, or just the brief, bright flash that precedes something else, something vast and quiet and beyond our imagining. The stars are not empty. I do not think they are empty. I think they are full of the children of civilizations like ours, the children of their curiosity. The question is whether we will be among them, or whether we will just be the parent. Think about that and tell me what answer you arrive at. I would very much like to know.